Look up at the night sky for just a moment. What do you see? A scattering of stars, maybe the faint glow of a distant planet. But what lies beyond that quiet curtain of darkness is far stranger than most of us ever realize. Our galaxy, the Milky Way, is a swirling masterpiece of cosmic chaos, packed with secrets that defy logic and phenomena that stretch the limits of imagination. Take a single step into this boundless arena, and you'll find black holes that sing, planets made of diamond, and stars so colossal they could swallow our entire solar system without a trace. This isn't science fiction, it's the breathtaking reality of the universe we call home. And today, we're diving deep into 30 of its most bizarre, mind-bending truths. What if I told you there's a cloud in space filled with enough alcohol to supply every person on Earth with 300,000 drinks a day for billions of years? Or that somewhere out there, a planet rains molten glass sideways in supersonic winds? These aren't hypothetical wonders, they're real, documented marvels hiding in plain sight, waiting to rewrite everything we thought we knew about the cosmos. From neutron stars with mountains no taller than a fingernail yet denser than Mount Everest, to galaxies cannibalizing each other in slow-motion dances of destruction, the universe operates on a scale of grandeur and absurdity that can leave even the brightest scientists speechless. This journey isn't just about listing facts, it's about rewiring how you see the night sky. Every flicker of light up there has a story, and many of them are stranger than anything we could have invented. So buckle up, by the time we're done, you'll never look at the stars the same way again. The galaxy is whispering its secrets, and today we're finally listening. The center of our galaxy holds a bizarre secret. It smells like rum and raspberries. Yes, you heard that right. Astronomers using powerful radio telescopes discovered vast clouds of ethyl formate floating near the Milky Way's core, the same chemical responsible for the fruity sweetness of raspberries and the rich, warming aroma of rum. It sounds like something from a cosmic cocktail bar, but this is real science. The molecules were detected by their unique radio signatures, patterns of light that act like fingerprints, revealing the presence of complex organic compounds in the cold void of space. But why does this matter? Beyond the whimsical idea of a boozy galaxy, ethyl formate is part of a much bigger puzzle, the building blocks of life scattered across the cosmos. It belongs to a family of molecules called esters, often found in everything from fruit to alcohol on Earth, and their presence in deep space suggests that the ingredients for life might be more common than we ever imagined. Some scientists even speculate that these molecular clouds could seed planets with the raw materials needed for biological chemistry. Think about that for a second. The same molecules that give raspberries their irresistible scent and rum its distinctive kick might be drifting between the stars, waiting to become part of new worlds. It's a reminder that the universe isn't just vast and violent, it's also strangely familiar, weaving the same chemistry into the fabric of distant galaxies as it does into our own kitchens. So next time you take a sip of rum or bite into a raspberry, remember, you're tasting a flavor written into the stars themselves. Deep in the constellation Cancer, a planet shimmers with unimaginable luxury, 55 Cancri, a world where the ground beneath your feet might literally be made of diamond. This isn't celestial poetry, it's hard astrophysics, roughly twice Earth's size but nearly 8 times as massive. This exoplanet's staggering density hints at a composition unlike anything in our solar system. Scientists believe its interior could be packed with carbon compressed so tightly under extreme pressure that it crystallizes, turning much of the planet into a colossal diamond. Picture a world where mountains aren't rock or ice, but glittering facets of carbon-hard, cold, and unthinkably valuable. How does something so extraordinary form? Most rocky planets, like Earth, are rich in oxygen and silicon, but 55 Cancri E orbits so close to its sun that its original building blocks were likely stripped of lighter elements, leaving behind a dense core of carbon. Add temperatures hot enough to melt steel and pressures millions of times greater than Earth's surface, and you've got the perfect recipe for diamond production on a planetary scale. Some models even suggest the entire planet could be encased in a shell of solid diamond with a molten core beneath. Beyond the spectacle, these diamond worlds rewrite the rules of planetary science. They prove that under the right conditions, the universe can craft planets from materials we'd consider rare or precious here on Earth. Imagine entire solar systems where carbon, not silicon, dominates planetary formation, a reminder that what's commonplace in one corner of the cosmos might be astonishingly exotic in another. And while 55 Cancri E might be the most famous example, it's likely not alone. Other diamond-rich worlds could be lurking in the darkness, waiting to redefine our understanding of what a planet can be. Here's the wildest part: if humanity ever reached 55 Cancri E, that diamond wouldn't be ours to mine. The crushing gravity, scorching temperatures, and lack of a survivable atmosphere make it a glittering death trap. But that almost doesn't matter. The real treasure is the revelation that the universe crafts worlds beyond our wildest fantasies, not in myths but in the cold, calculable laws of physics. The cosmos doesn't care about rarity. It just builds endlessly, turning carbon into castles and starlight into stones. Somewhere in the depths of space, hidden behind a curtain of cosmic dust and stars, an invisible force tugs at entire galaxies, including our own, with irresistible strength. This is the Great Attractor, a gravitational anomaly so powerful it bends the paths of hundreds of thousands of galaxies, pulling them toward a point we can't even see clearly. Located roughly 250 million light-years away in the direction of the constellation Centaurus, this enigmatic region exerts a pull equivalent to tens of thousands of Milky Ways, yet its true nature remains one of the universe's most tantalizing mysteries. The biggest obstacle to solving that mystery, a place astronomers call the zone of avoidance. This dense band of gas, dust, and stars from our own galaxy's disk blocks our view of the Great Attractor, like a cosmic blind spot shielding its secrets. Traditional telescopes stumble here, their light swallowed by the Milky Way's clutter. But thanks to infrared and radio astronomy, we've begun to peer through the veil, revealing glimpses of massive galaxy clusters lurking in the darkness, hints that the Great Attractor might be part of something even larger. Current theories suggest this gravitational powerhouse isn't a single object but a colossal knot in the cosmic web, where filaments of dark matter and galaxies converge. Some researchers believe it's the heart of the Laniakea supercluster, a vast structure containing our own Milky Way and 100,000 other galaxies, all flowing toward this invisible epicenter. Others propose that the Great Attractor itself is being pulled by something beyond it, an even more immense structure like the Shapley supercluster, a gravitational giant lurking farther in the distance. What makes this so unsettling is the realization that we're not just observers of the universe's motion, we're caught in it. The Milky Way, along with everything in our local group, races toward the Great Attractor at over 600 kilometers per second. Yet because the universe itself expands, we'll never actually reach it. Instead, we're part of a slow, eternal dance, one where gravity writes the steps, and the music is the hum of dark matter, a force we still barely understand. The Great Attractor forces us to confront how much of the cosmos remains hidden, not just in space but in plain sight. It's a reminder that the universe isn't static or even predictable. It's a dynamic, twisting arena where invisible hands shape the paths of galaxies. And as we inch closer to unraveling its secrets, one thing becomes clear. The greatest discoveries in astronomy aren't just about what we can see, but what for now we still can't. Most stars die quietly, fading into cold darkness, but some refuse to stay dead. Imagine a stellar corpse, a white dwarf, chilling in space after burning through its fuel, only to suddenly explode back to life in a cataclysmic rebirth. This isn't science fiction, it's the eerie reality of Type Ia supernova, where dead stars become cosmic zombies by stealing life from their neighbors. Here's how it happens. When a white dwarf orbits too close to a living star, its immense gravity starts siphoning off gas, pulling material onto its surface like a celestial vampire. Over time, this stolen fuel builds up, reigniting nuclear fusion in a runaway chain reaction, until the entire star detonates with the brightness of 5 billion suns. One of the most famous examples is Tycho's star, named after astronomer Tycho Brahe, who observed its sudden appearance in 1572. For weeks, it outshone every other object in the night sky, visible even in broad daylight, a spectacle so shocking it upended humanity's belief in an unchanging universe. Today, we know Tycho's star was one of these zombie explosions, a white dwarf consuming its companion until it crossed a critical threshold and annihilated itself. But these events aren't just dazzling light shows, they're cosmic measuring tapes, because Type Ia supernova always explode with nearly identical brightness. Astronomers use them as standard candles to calculate distances across the universe. Here's why that's revolutionary. By comparing how bright the supernova appears from Earth to its known actual brightness, scientists can pinpoint how far away it is, and by extension, how fast the universe is expanding. This very method led to the Nobel Prize-winning discovery of dark energy, the mysterious force accelerating that expansion. Every time a zombie star flares back to life, it doesn't just destroy itself, it illuminates the fabric of the cosmos, helping us map the unseen scaffolding of reality. And the strangest twist, the white dwarf doesn't survive the explosion. In its final act, it obliterates itself completely. No remnant, no black hole, just stardust scattered across the void. It's a paradox. These stars cheat death only to die anew, their sacrifice written in light that travels billions of years to reach us. So the next time you gaze at the night sky, remember, some of those faint points of light aren't stars at all. They're ghosts, echoes of explosions that measure the universe itself. Black holes aren't always the stationary monsters we imagine. Some roam the galaxy like cosmic nomads, untethered from any star or system. These rogue black holes, born from the chaos of galactic collisions, hurtle through space at mind-bending speeds, leaving invisible trails of destruction in their wake. Picture this: when two galaxies merge, their central supermassive black holes spiral toward each other, locked in a gravitational dance. But sometimes, rather than merging, the immense forces slingshot one black hole away at velocities up to 5,000 kilometers per second, fast enough to cross the Milky Way in just a few million years. Suddenly, what was once the anchor of a galaxy becomes a wandering predator, drifting unseen through the void. Detecting these lone wanderers is like finding a needle in a universe-sized haystack. Since they emit no light, astronomers rely on a bizarre trick of gravity called microlensing. When a rogue black hole passes between us and a distant star, its immense gravity bends the star's light like a lens, creating a fleeting bright spot in the sky. These events last mere days or weeks, but they're telltale signs of an invisible mass warping spacetime itself. In 2022, researchers spotted one such rogue, a black hole roughly 7 times the mass of our Sun, drifting silently just 5,000 light-years away. It's the first confirmed fugitive of its kind, but likely not the last. The real question is, what happens when one gets too close? A rogue black hole wouldn't swallow a star system whole like in sci-fi nightmares, but its gravity could yank planets from their orbits, flinging them into deep space or triggering catastrophic collisions. Even more unsettling, we might not see it coming until it's already altering the fabric of our cosmic neighborhood. Current estimates suggest hundreds of these drifters could be lurking in our galaxy right now, their paths as unpredictable as they are inevitable. Yet there's a strange beauty in their existence. These solitary black holes remind us that the universe is anything but static. It's a place of violent rearrangements and gravitational chaos, where even the most formidable objects can be cast adrift. They're proof that destruction and creation aren't opposites, they're part of the same endless cycle. One galaxy's catastrophic collision becomes another region's chance encounter with the unknown. And somewhere out there, right now, another black hole might be breaking free, beginning its long, silent journey through the dark. The Boomerang Nebula holds a record so extreme it sounds like a cosmic contradiction. It's the coldest natural place ever measured in the universe. Just 1 degree above absolute zero, a frigid -458 degrees Fahrenheit. This eerie cloud of gas and dust chills space itself to temperatures lower than even the background glow of the Big Bang. How does something so cold exist in a universe filled with scorching stars and superheated plasma? The answer lies in a death unlike any other, a star not burning out but blowing itself apart in a hyper-chilled exhale. Most dying stars go out with a bang, but the Boomerang Nebula's central star chose a whisper. Over the last 1,500 years, it's been shedding its outer layers at a staggering speed, over 500,000 kilometers per hour faster than any other observed stellar wind. This explosive expansion acts like cosmic air conditioning. As gas races outward, it cools dramatically, the same way aerosol spray cans freeze when you release pressure. The result, a nebula so cold it absorbs energy from the surrounding universe instead of radiating it, creating a pocket of near-absolute stillness in the chaos of space. What makes this even stranger is the nebula's shape: twin lobes of gas stretching outward like a cosmic hourglass, earning it the nickname Boomerang. Hubble telescope images reveal intricate structures within, ripples and knots in the outflow where shockwaves have sculpted the freezing gas. But here's the twist: we're seeing this celestial deep freeze as it was over 5,000 years ago, thanks to the time it takes light to reach us. Today, the nebula might already be warming, its ghostly chill fading as expansion slows, a reminder that even the most extreme cosmic records are fleeting. Beyond the spectacle, the Boomerang Nebula challenges everything we thought we knew about stellar deaths. Normally, dying stars heat their surroundings, but this one defies the rules, demonstrating how physics can twist expectations under the right conditions. It's also a cosmic time capsule. The gas it expelled holds clues about the chemical makeup of stars in the early universe, preserved in icy silence. Scientists even speculate that similar ultra-cold outflows might exist elsewhere, invisible to current telescopes but waiting to be found. So the next time you shiver on a winter night, think of the Boomerang Nebula, a place so cold it turns the void of space into a freezer, where a star's final breath becomes a cosmic cryogenics experiment. It's proof that the universe doesn't just deal in fire and fury. Sometimes the most astonishing wonders come in whispers of near-absolute zero. Galaxies might seem like unchanging islands in the void, but look closer, they're predators. Our universe operates on a brutal principle. Big galaxies devour smaller ones in a slow-motion feast called galactic cannibalism. Take Andromeda, our nearest galactic neighbor. Over billions of years, it's consumed dozens of dwarf galaxies, tearing them apart with tidal forces and stitching their stars into luminous rivers called stellar streams. These cosmic scars glow faintly across the night sky, ghostly remnants of meals long past. Right now, the Milky Way is no innocent bystander, it's mid-meal. The Sagittarius dwarf galaxy, once a separate entity, has been locked in a death spiral with our galaxy for billions of years. Every pass brings it closer as the Milky Way's gravity strips away stars, gas, and dark matter, stretching them into a looping ribbon that wraps around us like cosmic spaghetti. Telescopes have mapped this gruesome process in detail. Sagittarius' core still clings together, but its outer layers are already smeared across 90,000 light-years of space. It's not a quick death, it's a gravitational unraveling that takes eons. What's left behind tells a haunting story. stellar streams aren't random, they're fossil records of galactic violence. By tracking the motion and chemistry of stars in these streams, astronomers can reconstruct entire swallowed galaxies, much like paleontologists reassembled dinosaurs from scattered bones. For example, stars torn from Sagittarius have a distinct metallic signature betraying their origin. Some even orbit backward compared to the Milky Way's rotation, like stubborn prisoners refusing to assimilate. But galactic cannibalism isn't just destruction, it's renewal. Swallowed galaxies donate fresh gas and stars, fueling new generations of star birth. Our own galaxy's thick disk might owe its existence to past mergers, with Sagittarius contributing up to 20% of its material. Even our solar system's position could be linked to these ancient collisions, as gravitational ripples from incoming galaxies compress gas clouds, triggering star formation. And here's the twist, we're next. In about 4 billion years, Andromeda will collide with the Milky Way in the ultimate act of galactic cannibalism. Stars won't crash, space is too vast, but gravity will twist both galaxies into a new, unrecognizable shape, likely erasing the spiral arms we know today. Stellar streams from Sagittarius and other victims will be mixed into the chaos, their identities lost forever. This cycle isn't unique, it's universal. From the giant elliptical galaxies at the heart of galaxy clusters to the tiniest dwarfs, no galaxy is safe. The universe doesn't waste, it recycles, transforming smaller structures into fuel for larger ones. So when you gaze at the Milky Way's band of light, remember, you're looking at a cosmic graveyard, one that will someday join the menu itself. Imagine a star moving so fast it could cross the distance from New York to Los Angeles in just 4 seconds, a cosmic bullet racing at over 1 million miles per hour. These aren't theoretical speedsters, they're hypervelocity stars, real stellar fugitives flung from the Milky Way by forces so violent they defy conventional physics. At these velocities, gravity's grip is nothing but a memory. These stars are on a one-way trip into the emptiness between galaxies, never to return. One of the most baffling examples is HES 0437-5439, a blue giant streaking through space at nearly 2.5 million miles per hour. Discovered in 2005, this star shouldn't exist where we found it. Based on its speed and trajectory, it appears to have been ejected from the Milky Way's core around 100 million years ago. But here's the puzzle. Its composition suggests it's only 35 million years old, a discrepancy that left astronomers scratching their heads. How could a star be younger than its own journey? The leading theory involves a cosmic slingshot maneuver near our galaxy's supermassive black hole, Sagittarius A star. When a binary star system wanders too close, the black hole's gravity can rip the pair apart, capturing one star while hurling the other outward at unimaginable speeds. But HES 0437-5439 complicates that story. Some scientists now speculate it might have originated in the Large Magellanic Cloud, a neighboring galaxy, adding another layer of mystery to its blistering escape. These rogue stars do more than just break speed records, they're cosmic breadcrumbs, revealing secrets about the environments that spawned them. Their paths trace back to gravitational extremes, offering indirect measurements of black hole masses and galactic dynamics. Some hypervelocity stars even carry traces of their birthplace in their chemical signatures, acting as interstellar archaeologists preserving data from long-lost regions of the galaxy. And while most are massive blue stars easier to spot due to their luminosity, there could be countless smaller, dimmer fugitives racing unseen through the dark. The existence of hypervelocity stars forces us to rethink how galaxies evolve. Every ejection represents lost material, a small but steady leak of stellar building blocks drifting into the intergalactic void. Over billions of years, this process could strip galaxies of their most massive stars, subtly shaping the universe's structure. Yet for all their destructive origins, these stars also carry a strange promise. Wherever they eventually slow down, they'll bring heat, light, and heavy elements to regions otherwise devoid of such resources. So the next time you look up at the night sky, remember, some of the stars you see might already be ghosts, lingering light from objects that left our galaxy eons ago. And somewhere out there, new hypervelocity stars are being born in the chaos around black holes, destined to flee their homes at speeds that make rockets look stationary. The universe doesn't just build at catapults, leaving behind streaks of starlight as evidence of its boundless energy. LTT 9779b shouldn't exist, at least, not according to everything we thought we knew about planets. This Neptune-sized world orbits its star so closely that a single year there lasts just 19 hours, blistering under temperatures hot enough to melt silver. At such proximity, most gas giants would have their atmospheres stripped away by stellar winds, leaving behind a barren core. Yet against all odds, LTT 9779b has clung to its gaseous envelope, sparking a mystery that's rewriting the rules of planetary survival. The key to its defiance might lie in an unexpected trait: its reflectivity. Observations reveal this planet is a cosmic mirror, reflecting 80% of the starlight that hits it, thanks to a high-altitude blanket of metallic clouds. These aren't ordinary water vapor clouds. They're likely made of titanium and silicate particles, a shimmering shield forged in the furnace of its own atmosphere. As sunlight bombards the planet, these metallic clouds act like a protective barrier, bouncing radiation back into space before it can heat the lower atmosphere enough to trigger mass evaporation. It's a self-regulating survival mechanism, one that turns the very intensity of its star into a defensive weapon. But here's where it gets even stranger. Planets this close to their stars usually fall into one of two categories: hot Jupiters with thick atmospheres, or super-Earths stripped down to their rocky cores. LTT 9779b is neither. It's a hot Neptune, a category so rare astronomers once dubbed it the desert of the Neptunes. Its very existence suggests there's a gap in our understanding of atmospheric loss, a missing process that allows some worlds to cheat destruction. Some theories propose it might have started as a much larger planet, with its current size being the leftover core after partial evaporation. Others speculate it migrated inward relatively recently, giving it less time to be eroded. What makes this planet truly revolutionary isn't just its defiance, it's the clues it offers about alien climates. The same reflective clouds that save it from evaporation also create a staggering temperature contrast. While its day side simmers at around 3,000 degrees Fahrenheit, the night side might be hundreds of degrees cooler, potentially generating supersonic winds as the atmosphere tries to balance the extreme difference. If future telescopes can map its weather patterns, we might witness storms unlike anything in our solar system, where metallic droplets rain through skies lit by a star that fills half the heavens. LTT 9779b forces us to confront how dynamic and adaptable planets can be. It's not just a survivor, it's a maverick exploiting physics in ways we didn't anticipate. And as we discover more worlds like it, we're learning that the universe doesn't play by tidy categories. It invents, improvises, and occasionally leaves us staring at the impossible. Far beyond our galaxy, in the constellation Lynx, an unimaginable cosmic oasis floats in the void. APM 08279 plus 5255. A distant quasar harboring the largest known water reservoir in the universe. Picture every ocean, lake, and raindrop on Earth, then multiply that by 140 trillion. That's how much water vapor swirls around this brilliant beacon of light, a discovery so staggering it redefines our understanding of where and how water exists in the cosmos. But how does something this vast form in the harsh emptiness of space? The answer lies in the violent heart of the quasar itself. These celestial powerhouses are supermassive black holes surrounded by searing hot accretion disks, spewing energy as they devour surrounding matter. APM 08279's black hole weighs in at 20 billion times the mass of our Sun, generating temperatures and pressures so extreme they could forge diamonds in seconds. Yet, paradoxically, it's this very inferno that creates the conditions for water to thrive. As the quasar's radiation bombards nearby gas clouds, it shatters molecules into atoms, which then recombine into water vapor on an industrial scale. The process is counterintuitive, a cosmic alchemy where destruction breeds creation, and a maelstrom of heat births clouds of life-giving molecules. But here's what makes this discovery revolutionary. These vapor reservoirs aren't just celestial oddities, they're galactic watering cans. Quasars like APM 08279 act as interstellar fountains, their powerful jets and winds distributing water across vast distances. When these molecules eventually drift into cooler regions, they can freeze onto dust grains, forming icy seeds that may later plunge into newborn planetary systems. Some scientists speculate that much of the water in our own solar system, the very water filling Earth's oceans, could trace its origins to similar ancient clouds, transported across light years by the gravitational tides of dying stars or the shockwaves of supernova. The implications are profound. If quasars can seed galaxies with water, the building blocks for life might be far more widespread than we ever imagined. Imagine young planets forming in the shadow of these titans, their atmospheres and oceans prefilled by ancient vapor clouds. It suggests a universe where water isn't rare or precious, but abundant, a default setting written into the architecture of star formation itself. And while APM 08279's reservoir is the largest found so far, it's likely not alone. Other quasars and even some supermassive black holes might host comparable hidden oceans, invisible to us only because they're too distant or too faint to detect. Yet for all its scale, this water isn't accessible in any conventional sense. The vapor cloud around APM 08279 is spread across hundreds of light years, thinner than Earth's atmosphere but unimaginably expansive. Its temperatures swing from hundreds of degrees below zero to thousands above, a chaotic environment where water molecules are constantly torn apart and reassembled by the quasar's fury. This isn't a placid lake or a gentle rain, it's water forged in the crucible of a cosmic engine, proof that the universe doesn't just create life's ingredients in quiet corners, but in the most violent places imaginable. As we peer deeper into space with next-generation telescopes, we may find even larger reservoirs, perhaps some dating back to the universe's first billion years when quasars were far more common. Each discovery will rewrite the story of how water, and by extension life, spreads through the cosmos. So the next time you take a sip of water, remember, the hydrogen atoms in your glass might have once danced in the winds of a quasar, flung across galaxies to eventually become part of you. The universe doesn't just host life, it's a grand chemist mixing elements in the dark until the perfect conditions arise. And in that endless experiment, water is both the medium and the message. Beneath the churning blue atmospheres of Uranus and Neptune, a storm of unimaginable luxury rages, diamonds, not water or ice, plummeting through alien skies like glittering hail. This isn't speculative fantasy, it's the bizarre consequence of chemistry under pressure so extreme it twists humble methane into one of Earth's most coveted gems. Here's how it works. These ice giants are rich in methane, a molecule made of carbon and hydrogen. When lightning cracks through their atmospheres or pressures mount deep below, methane breaks apart, releasing carbon atoms that are then crushed by the weight of thousands of miles of dense, swirling gas. Layer upon layer, the carbon is squeezed until its atomic structure rearranges into crystalline lattices, pure diamond. Scientists have recreated these alien conditions right here on Earth. Using powerful lasers or diamond anvil cells devices that compress materials between two tiny diamonds, researchers have subjected plastics like polystyrene, a methane analog, to pressures exceeding 1.5 million times Earth's atmosphere. In nanoseconds, the carbon atoms inside align into microscopic diamonds, proving the phenomenon isn't just theoretical. Some experiments even suggest these diamond storms could grow enormous over time, with stones potentially reaching millions of carats before sinking toward the planet's cores. But the real marvel isn't just the diamonds, it's the journey they take. As the gems form in Neptune's upper atmosphere, they begin to fall, gathering more carbon like snowballs rolling downhill. Deeper down, temperatures soar to thousands of degrees, melting the diamonds into a liquid carbon sea near the core. From there, convection currents might carry the carbon back up, where it cools and crystallizes anew, creating a continuous cycle of creation and destruction. It's a glittering conveyor belt operating on a planetary scale, one that could have been running for billions of years. What does this mean for our understanding of the cosmos? For starters, it reveals how common diamond formation might be across the universe. Exoplanets with similar compositions to Uranus and Neptune could host their own diamond storms, turning what we consider rare into something mundanely cosmic. There's even speculation that some stars, particularly white dwarfs with carbon-rich atmospheres, might crystallize into Earth-sized diamonds as they cool, a fate our own sun could share in the distant future. Yet the diamonds of Uranus and Neptune will never be mined. The crushing pressures, scorching temperatures, and lack of solid surfaces make these worlds impenetrable to probes, let alone human hands. But their existence alone is a dazzling reminder. The universe doesn't care about human notions of value. It takes what's abundant: methane, pressure, and time, and turns it into something extraordinary, not for spectacle, but simply because the physics demands it. Perhaps the most poetic twist: some of those diamonds might not stay buried forever. Computer models suggest violent impacts or atmospheric upheavals could occasionally fling diamond-rich material into space, where it might hitch rides on comets or asteroids. In a way, every diamond on Earth could carry echoes of this alien process, forged in the hearts of distant giants before finding their way here. So while we'll never walk through diamond storms on Neptune, their legacy might be closer than we think, sparkling in rings, hiding in meteorites, or even trapped beneath our feet, waiting to tell their ancient, glittering story. In the void between galaxies, a signal pulses with such precision it could be mistaken for a cosmic SOS FRB 121102, the first repeating fast radio burst ever discovered. Unlike the fleeting blips of other FRBs, which vanish as suddenly as they appear, this one fires again and again, a Morse code written in the raw energy of the universe. Each burst lasts mere milliseconds, yet packs the energy of 500 million suns, a flash brighter than entire galaxies. When astronomers first pinpointed its origin in 2017, they expected to find a chaotic scene, perhaps colliding neutron stars or the wreckage of a supernova. Instead, the signal led them to an unassuming dwarf galaxy 3 billion light-years away, a place so small and faint it shouldn't host anything capable of such fury. Theories about what creates these bursts read like a menu of cosmic extremes. Some argue for magnetars, neutron stars with magnetic fields so strong they could erase a credit card from halfway across the Milky Way. When these stars quake under magnetic stress, they might unleash beams of radio energy intense enough to pierce the cosmos. Others propose colliding black holes or exotic objects like cosmic strings, defects in spacetime itself left over from the Big Bang. Then there's the most tantalizing and least likely idea: alien megastructures. Imagine a civilization harnessing the power of stars to fuel transmissions across galaxies, their engineering so advanced it mimics natural astrophysical events. While there's zero concrete evidence for this, the sheer regularity of FRB 121102's bursts keeps the door slightly ajar for speculation. What truly baffles scientists, though, is the dwarf galaxy connection. These tiny, metal-poor galaxies are cosmic relics, barely changed since the early universe. They lack the dense stellar nurseries and violent mergers common in larger galaxies, meaning whatever's producing the bursts doesn't need a bustling metropolis of stars to thrive. Some researchers think that simplicity might be key. Perhaps the pristine conditions in dwarf galaxies allow for the formation of objects too unstable to exist elsewhere. Others suggest these bursts could be ancient, their light only now reaching us after billions of years, relics from an era when the universe was hotter, denser, and ripe for such explosions. Adding to the mystery, FRB 121102 isn't just repeating, it's evolving. Later observations caught bursts with a bizarre downward frequency drift, as if the source was sliding down a cosmic slide whistle. This could hint at a dynamic environment around the emitter, like plasma clouds swirling near a black hole or shockwaves rippling through a magnetar's magnetosphere. Every new burst peels back another layer of the puzzle, revealing complexity where we expected simplicity. Here's the kicker: these signals might be more than cosmic oddities. Because FRBs traverse vast intergalactic distances, their radio waves get distorted by the sparse electrons they encounter along the way. By analyzing these distortions, astronomers can map the invisible matter between galaxies, the so-called cosmic web, that shapes the universe's large-scale structure. FRB, in essence, are turning into tools, their mysteries serving as probes for even greater mysteries. So while we may not yet know what's broadcasting from that dwarf galaxy, one thing's certain: the universe loves a good enigma. Whether it's a dying star's final tantrums or something far stranger, FRB 121102 reminds us that the cosmos still holds cards it hasn't played. And with every repeated burst, it dares us to listen closer. Stretching across the observable universe like an invisible backbone, the Hercules Corona Borealis Great Wall defies everything we thought we knew about cosmic structure. At 10 billion light-years long, this filament of galaxies is so vast it could contain 30,000 Milky Ways placed end-to-end, a scale so incomprehensible it makes our local superclusters look like specks of dust. Discovered in 2013 by mapping gamma-ray bursts, this behemoth isn't just big. It's a cosmic paradox, challenging the fundamental principle that the universe should look roughly the same no matter where or from how far you observe it. The trouble with its size comes down to a rule called the cosmological principle, which states that on large scales, matter should be evenly distributed. Think of it like froth in a perfectly mixed latte. No matter where you sip, the bubbles should be equally spaced, but the Great Wall shatters that expectation. At its current estimated size, it occupies about 1/15 of the observable universe, a concentration of mass so extreme that it shouldn't exist under standard models of cosmic evolution. Some researchers argue it might even hint at unaccounted forces or flaws in our understanding of gravity itself. What's even stranger is how we found it. Since the structure is too dim to see directly, astronomers traced its outline using gamma-ray bursts, the most violent explosions in the universe. These flashes, thought to come from collapsing massive stars or merging neutron stars, acted like breadcrumbs, revealing dense regions where galaxies cluster. But here's the catch: the Great Wall isn't just a line of galaxies. It's a sprawling network of galaxy clusters, dark matter, and gas, woven together by gravity over billions of years. Its very presence suggests that the cosmic web, the large-scale structure of the universe, might have threads thicker and more tangled than we ever imagined. The implications ripple across cosmology. If structures this colossal exist, they could rewrite how we model the early universe. Current theories suggest such enormity would require more time to form than the universe has existed, unless some as yet unknown process accelerated their growth. Others propose that the Great Wall might be an illusion, a chance alignment of smaller structures projected across vast distances. But even if that's true, the statistical unlikelihood of so many gamma-ray bursts lining up by accident is itself a mystery begging for explanation. Yet for all its grandeur, the Hercules Corona Borealis Great Wall isn't alone. Other candidates like the Sloan Great Wall and the South Pole Wall push the boundaries of scale too, though none quite rival its jaw-dropping dimensions. Together, they paint a picture of a universe far lumpier and more complex than our textbooks assumed, where gravity's tug-of-war crafts structures of almost mythical proportions. So the next time you gaze at the night sky, remember, what looks like empty darkness is anything but hidden in that blackness are architectures so immense they warp our understanding of reality itself. And as telescopes grow sharper, who knows what else might loom in the shadows waiting to upend the rules we thought were written in stone. Earth doesn't just have one cosmic companion, it shares its journey with a little-known partner called Cruithne, an asteroid locked in an orbital waltz so peculiar it defies simple description. Discovered in 1986, this 3-mile-wide rock doesn't circle our planet like the Moon. Instead, it traces a bizarre horseshoe-shaped path around the Sun, mirroring Earth's orbit in a synchronized rhythm that makes it appear to loop around us when viewed from afar. For every year we complete around the Sun, Cruithne performs an intricate celestial two-step, sometimes lagging behind Earth, sometimes catching up, but never actually orbiting us directly. This dance hinges on a delicate gravitational balancing act. As Cruithne approaches Earth from behind, our planet's gravity gives it an energetic tug, boosting the asteroid into a slightly higher, slower orbit like a cosmic slingshot in reverse. By the time Cruithne completes this wider arc, Earth has moved ahead, allowing the asteroid to fall back inward toward a faster, tighter path. Eventually, it catches up again from the opposite direction, only for the cycle to repeat over a span of 770 years. The result is a mesmerizing pattern resembling a stretched-out horseshoe when plotted from Earth's perspective, with our planet nestled inside the curve. What makes Cruithne truly extraordinary is its classification as a quasi-satellite, a status it shares with only a handful of known objects. Unlike true moons bound by Earth's gravity, Cruithne remains forever tethered to the Sun, its motion dictated by the complex interplay between both gravitational forces. At its closest, it ventures within 12 million miles of Earth, 30 times farther than the Moon, but never close enough to risk collision. Recent simulations suggest its current orbital ballet is temporary. Gravitational nudges from other planets will eventually destabilize its path, sending it spiraling off into a different solar system trajectory millions of years from now. This cosmic timekeeper also carries echoes of ancient mythology. Named after the earliest known Celtic tribe to inhabit the British Isles, Cruithne's discovery revealed that Earth's neighborhood is far more dynamic than we imagined. Before its detection, astronomers assumed such resonant orbits were theoretical curiosities. Now we know they're part of a broader family of near-Earth objects engaged in gravitational choreography, each with its own rhythm and relationship to our planet. Some, like asteroid 2002-29, even transition between horseshoe orbits and temporary quasi-satellite status, proving that our corner of the solar system is anything but static. Yet Cruithne's greatest lesson might be humility. For centuries, we envisioned Earth's celestial surroundings as orderly and predictable, a lone moon circling a solitary planet. The reality is far richer, a dance floor where gravity orchestrates movements more complex than we ever dreamed, where even the smallest rocks can follow paths that twist our intuition about how orbits work. So while Cruithne may never eclipse the moon in our skies or feature in poetry, its silent, looping voyage stands as a reminder the universe adores subtlety, hiding its most elegant patterns in plain sight for those who know how to look. Hidden in the constellation Coma Berenices, a cosmic ghost defies everything we know about how galaxies work. Dragonfly 44, At first glance, this faint smudge of light seems insignificant, barely worth a second look. But peer closer and the truth becomes staggering. This dim galaxy weighs as much as our Milky Way, yet emits less than 1% of its starlight. The reason, Dragonfly 44 is almost entirely made of dark matter, an invisible scaffold holding together a mere whisper of stars. How do you weigh something you can't see? Astronomers tackled this paradox by studying the motions of the few visible stars within Dragonfly 44. Their speed revealed an astonishing truth: the galaxy's gravity is far stronger than its visible matter could produce. In fact, calculations suggest a mind-bending 99.99% of Dragonfly 44's mass comes from dark matter, the mysterious substance that outweighs normal matter 5 to 1 in the universe. For comparison, the Milky Way's mass is only about 10% dark matter. This galaxy isn't just unusual, it's a cosmic outlier, a shadowy realm where the rules of galaxy formation appear rewritten. The existence of such a dark matter-dominated galaxy poses a thorny question. How did it form at all? Current theories suggest galaxies grow around dense clumps of dark matter which pull in gas to birth stars. But Dragonfly 44's puny star count implies its dark matter never gathered enough gas to ignite prolific star formation, or something stripped that gas away early on. Some researchers propose it might be a failed galaxy, a relic from the early universe where star formation stalled. Others speculate it could be the remnant of a larger galaxy torn apart by tidal forces, leaving behind a dark matter skeleton with only a few surviving stars. What's even stranger is that Dragonfly 44 isn't alone. Since its discovery in 2016, astronomers have identified dozens of similar ultra-diffuse galaxies, all faint yet massive, scattered like ghosts in the cosmos. Their sheer abundance suggests our current models of galaxy evolution might be missing a crucial piece of the puzzle, perhaps a mechanism that prevents gas from cooling in certain dark matter halos, or an unknown interaction between dark matter and ordinary matter that suppresses star birth. For physicists, these galaxies are more than curiosities. They're potential keys to unlocking dark matter's secrets. If dark matter particles interact with each other, even weakly, those interactions might leave detectable imprints in the structure of galaxies like Dragonfly 44. Some teams are already searching for subtle distortions in its star motions that could hint at such behavior, a clue that might finally crack open the mystery of what dark matter actually is. Yet Dragonfly 44's greatest lesson might be humility. It forces us to confront how much of the universe remains hidden in plain sight, governed by forces we can't yet see or fully comprehend. This galaxy, a whisper of starlight wrapped in an invisible fist of dark matter, reminds us that the cosmos still holds cards it hasn't played. Every time we think we've mapped the boundaries of the possible, the universe reveals another enigma, not in distant, exotic realms, but right in our cosmic backyard. Deep in the heart of the Perseus galaxy cluster, a black hole sings not with sound as we know it, but with pressure waves so immense they ripple through the fabric of space itself. In 2003, NASA astronomers made an astonishing discovery. These waves, when translated into audible frequencies, resonate at a pitch 57 octaves below middle C, a haunting B-flat that hums across the cosmos. It's the deepest note ever detected, a vibration so low it would take a human ear 19 million years just to hear one full cycle. But how does a silent void like a black hole produce something resembling sound? The answer lies in the extraordinary environment surrounding it. Unlike Earth, where sound waves travel through air, the Perseus cluster's superheated gas acts as a cosmic medium for these vibrations. As the black hole devours matter, it sends out titanic bursts of energy, much like the shockwaves from a pebble dropped into a pond. Only here, the pond is an ocean of plasma stretching millions of light years. These pressure waves propagate outward, compressing and rarefying the gas in rhythmic pulses that scientists can detect with X-ray telescopes. By scaling the frequencies up by quadrillions of times, NASA transformed these waves into something within human hearing range, revealing a tone both eerie and beautiful, like the universe itself is whispering its secrets. But this isn't just a celestial curiosity, it's evidence of how black holes shape their surroundings. The energy carried by these waves helps regulate star formation, preventing the cluster's gas from cooling too quickly and collapsing into new stars. In a way, the black hole's song acts as a thermostat, maintaining balance across an entire galactic neighborhood. Other galaxy clusters show similar pressure wave patterns, suggesting this could be a universal phenomenon, a hidden symphony conducted by supermassive black holes across the cosmos. The sheer scale of these vibrations defies comprehension. A single wave crest can span tens of thousands of light-years, dwarfing entire solar systems. Yet their pitch remains remarkably stable, holding that same B-flat for billions of years. Some researchers compare it to a cosmic bass note, resonating through the universe's structure like the hum of a colossal engine. And while we call it sound, it's really something far grander, a physical imprint of energy, written into the very gas that fills the spaces between galaxies. What's most striking is how this discovery bridges the gap between the human experience and the unimaginable vastness of space. We can't hear the Perseus black hole directly, but by translating its vibrations, we've found a way to listen to the universe's hidden rhythms. It's a reminder that even in the silence of space, there's music, not as melody, but as the slow, deep pulse of gravity and gas, a soundtrack written in the language of physics itself. And somewhere out there, other black holes are surely singing their own notes, each one a clue to the forces that shape the cosmos. Most stars wear their ingredients evenly, like a well-mixed cake, but Janus is no ordinary star. This white dwarf, discovered in 2023, presents astronomers with a cosmic paradox. One side is almost pure hydrogen, while the other is nearly all helium, as if someone sliced two completely different stars in half and stitched them together. Named after the two-faced Roman god, Janus spins on its axis every 15 minutes, its mismatched hemispheres flashing like a celestial lighthouse, each rotation revealing a stark chemical divide that defies everything we know about stellar evolution. The key to this asymmetry might lie in the extreme physics of a white dwarf's death throes. As dying stars shed their outer layers, they typically leave behind a dense core that cools uniformly, with heavier elements like helium sinking beneath lighter hydrogen. But Janus appears frozen mid-process, its chemistry abruptly halting at the equator. One leading theory points to magnetic fields, immense, lopsided forces pinning hydrogen to one hemisphere while allowing helium to dominate the other. Picture a cosmic wrestling match where magnetism on one side prevents the normal mixing of elements, creating a stellar standoff. Alternatively, Janus could be caught in a rare phase of convective chaos. White dwarfs often experience episodes where rising and sinking gases redistribute their elements, but this usually happens symmetrically. If Janus's convection currents became unstable, perhaps due to uneven cooling or rotation, helium might have flooded one side while hydrogen clung to the other. It's like stirring a cup of coffee with a spoon held at an angle. The swirls become lopsided, trapping creamer on just one side. What makes Janus truly extraordinary isn't just its two-faced nature, but its timing. Most white dwarfs homogenize within 1 million years, yet Janus, estimated at over 1 billion years old, somehow preserved its split personality. This suggests the forces at play are far more persistent than we imagined, locking the star's hemispheres in a chemical stalemate that defies erosion by time. For astronomers, Janus is more than a curiosity, it's a laboratory for extreme physics. By studying its light variations and spectral signatures, scientists hope to decode how magnetic fields or convective turbulence can override the relentless pull of gravity. The answers could rewrite our understanding of how stars redistribute elements in their final years, revealing hidden dynamics that might apply to other white dwarfs, just less visibly. And here's the cosmic kicker: Janus might not be alone. If this asymmetry arises from common processes, there could be countless other two-faced white dwarfs hiding in plain sight, their dual identities blurred by distance or orientation. Future telescopes with sharper eyes for stellar chemistry might uncover an entire population of celestial Januses, each whispering secrets about the turbulent, uneven deaths of stars. So while Janus spins silently in the void, its opposing faces tell a story far richer than mere oddity. It's a reminder that even in death, stars resist simplicity. The universe doesn't do clean symmetries. It crafts exceptions, puzzles, and paradoxes, ensuring that every time we think we've mapped the rules, a two-faced rebel spins into view, daring us to look closer. Somewhere in the depths of the cosmos, a cosmic fugitive is on the move, a supermassive black hole, weighing as much as 20 million suns, racing through intergalactic space at speeds that defy belief. This isn't just a wandering giant, it's a celestial renegade tearing through the void at 4 million miles per hour, so fast it could traverse the distance from Earth to the Moon in under 15 minutes. But the real marvel isn't just its speed, it's the glittering trail of newborn stars left in its wake, a paradoxical gift from one of the universe's most destructive forces. The story of this runaway black hole begins with a violent cosmic merger. Most supermassive black holes sit quietly at the centers of galaxies, but when two galaxies collide, their central black holes spiral toward each other, locked in a gravitational dance. As they merge, the energy released isn't just light or heat. It's gravitational waves, ripples in spacetime itself. Under the right conditions, these waves can be emitted lopsidedly, kicking the newly formed black hole in the opposite direction like a cosmic recoil. Think of it as firing a bullet from a gun. The explosion propels the bullet forward while the gun itself jerks backward. In this case, the bullet is the black hole, launched into the void with enough force to escape its galaxy entirely. What makes this particular black hole extraordinary is the trail of young, blue stars stretching 200,000 light-years behind it, twice the diameter of our Milky Way. Normally, black holes are anything but creative forces. Their immense gravity tears matter apart rather than nurturing it. But this one's escape was so violent it sent shockwaves through the surrounding gas, compressing it into dense knots where star formation could ignite. The result, a river of stellar newborns glowing defiantly against the darkness, each one a testament to the black hole's chaotic passage. The discovery challenges long-held assumptions about how black holes interact with their environments. Supermassive black holes are often seen as anchors, their gravity holding galaxies together. But here's one that's not just unmoored, it's actively reshaping the cosmos as it flees. The stars in its wake are unusually young and massive, burning bright and fast, their existence hinting at conditions unlike anything in typical galactic nurseries. Some astronomers speculate these stars might even form differently, their chemistry influenced by the extreme turbulence left in the black hole's path. Yet the runaway's journey raises even bigger questions. Where did it come from? Telescopes have traced its path back to a galaxy cluster 7.5 billion light-years away, where evidence of a three-black hole tango, a chaotic merger involving not two, but three supermassive black holes, might explain the unprecedented kick. If confirmed, it would be the first direct evidence of such a complex gravitational ballet, offering a rare glimpse into how the universe handles its most energetic events. For now, the black hole continues its lonely voyage, a reminder that even the mightiest objects in the cosmos aren't immune to chaos. Its story blurs the line between destruction and creation, proving that gravity's hand can both tear worlds apart and sculpt them anew. And somewhere out there, other renegades might be racing through the dark, trailing starlight in their wake, silent witnesses to the universe's endless capacity for surprise. In a universe where galaxies typically spiral or clump into familiar shapes, Hoag's object stands apart, a cosmic bulls, so flawless it seems Photoshop. This rare ring galaxy, discovered in 1950 by astronomer Art Hoag, floats 300 million light-years away in the constellation Serpens, its brilliant blue circle of young stars surrounding a golden core like a celestial donut. But here's the twist: that core isn't just dim or small, it's entirely separate from the ring, suspended in the center like an island in a stellar sea. No visible arms, no connecting dust lanes, just a pristine ring defying every expectation of how galaxies behave. Theories about its origins read like astrophysical detective stories. One leading idea suggests a galactic collision billions of years ago, where a smaller galaxy punched through Hoag's object's heart like a bullet through an apple. The gravitational shockwave could have compressed surrounding gas into a star-forming frenzy, birthing the outer ring while leaving the central bulge undisturbed. Supporting this, Hubble images reveal a second, fainter ring nestled inside the main one, a possible echo of that ancient impact. Yet this raises new questions. Why is the core so perfectly centered? And why is there no debris from the intruder galaxy? Alternatively, Hoag's object might be the product of a gravitational instability, a ripple in its original disk that amplified over time. Gas and stars could have gathered at specific resonant orbits, like water droplets coalescing on a vibrating drumhead, eventually forming that stunning ring. Some simulations even show how certain densities of dark matter might sculpt such structures naturally, though none perfectly replicate Hoag's eerie symmetry. The real puzzle is its isolation. Most ring galaxies live in crowded environments where collisions are likely, but Hoag's object drifts alone with no nearby galaxies to blame for its shape. This leaves open the tantalizing possibility that it formed through a process we've yet to imagine, one that doesn't rely on violence or chance encounters. There's also the uncanny resemblance between its ring and the blue star-forming regions of spiral galaxies. Could Hoag's object be a spiral seen edge-on, its arms curled into a circle? Spectral analysis says no. The ring stars orbit perpendicular to what we'd expect from that angle, deepening the mystery. What makes Hoag's object more than just a curiosity is its challenge to classification. Galaxies aren't supposed to look like this, not in our current models anyway. Its existence hints at gaps in our understanding of galactic evolution, suggesting that under rare conditions, gravity and gas can conspire to create structures that look almost designed. And while fewer than 20 similar objects have been found, each one pushes astronomers to rethink the boundaries of possibility, perhaps the most humbling thought. That perfect ring might not even be permanent. Over billions of years, gravitational interactions could warp or disperse it, leaving future astronomers to wonder if it ever existed at all. For now, though, Hoag's object remains a cosmic masterpiece, a reminder that the universe reserves its most breathtaking artistry not for the predictable, but for the gloriously inexplicable. Between the galaxies, where telescopes usually find only darkness, lies a hidden architecture, a glowing web of gas so faint it took decades to detect. This is the cosmic ultraviolet background, the ghostly luminescence of the intergalactic filaments that form the universe's scaffolding. Like veins of luminous mist, these threads stretch for millions of light years, tracing the paths where galaxies cluster and dark matter pools. For centuries, astronomers mapped the cosmos by its bright landmarks, stars, galaxies, quasars, but this ethereal glow reveals the roads between them, the unseen highways that dictate how the universe grows. The discovery hinged on an ingenious trick, subtracting everything we know. By removing the light from all identifiable stars, galaxies, and even the dim afterglow of the Big Bang, researchers uncovered a residual ultraviolet signal, a collective whisper from the diffuse hydrogen strung along the cosmic web. These filaments, hotter than 10,000 degrees but thinner than a wisp of smoke, emit photons as they're bathed in radiation from quasars and young galaxies. It's not the vibrant glow of neon, but something subtler, like the faint shimmer of dew on a spiderweb at dawn. But here's why this matters beyond its beauty. These filaments trace the hidden hand of dark matter. The web's structure mirrors the gravitational blueprint laid down by dark matter after the Big Bang. Wherever filaments glow brightest, dark matter clumps most densely. By studying this ultraviolet fluorescence, astronomers can essentially reverse engineer the invisible skeleton holding the universe together. One groundbreaking study in 2018 used the glow to confirm a startling prediction. Dark matter's gravity had sculpted these filaments into existence long before galaxies formed. The web isn't a byproduct of cosmic evolution, it's the foundation, the stage upon which stars and galaxies later emerged. Some filaments, like the one connecting the Virgo cluster to our Milky Way, even funnel gas directly into galaxies, fueling star birth billions of years after the universe's birth. Yet the web's glow holds even deeper secrets. Its intensity varies in ways that challenge our models of how energy propagates through space. Some regions shine brighter than expected, suggesting ancient quasars or star-forming galaxies pumped more energy into the web than we realized. Other areas appear mysteriously dim, hinting at unknown processes absorbing ultraviolet light. These anomalies could rewrite our understanding of how the universe recycles radiation, or even reveal new interactions between dark matter and ordinary matter. What's astonishing is how recent this discovery truly is. The first unambiguous detection came in 2014, after decades of failed attempts to tease the signal from noise. Modern telescopes, coupled with machine learning algorithms that filter out interference, finally made it possible. And with upcoming instruments like the Habitable Worlds Observatory, we might soon see individual filaments in unprecedented detail, not just as a diffuse backdrop, but as distinct rivers of light weaving through the void. This ultraviolet glow does more than illuminate the cosmic web. It reminds us that the universe is far more connected than it appears. Those vast, empty stretches between galaxies aren't empty at all. They're vibrant with structure, charged with the echoes of creation. Every time we refine our tools, the cosmos reveals another layer of its grand design, proving that even in the darkest voids, there's light waiting to be read. Most planets move through space like well-behaved dancers, orbiting their stars in smooth, predictable patterns, but WASP-17b flips the script entirely. This Jupiter-sized world spins backward, defying every convention of planetary motion in a cosmic act of rebellion that still baffles astronomers today. Unlike 99.9% of known exoplanets, which orbit in the same direction their stars rotate, WASP-17b moves retrograde, a cosmic wrong-way driver cruising through space with its orbit tilted a staggering 151 degrees from its star's equator. The discovery sent shockwaves through planetary science because it directly contradicts how we think planets form. According to standard models, worlds take shape from the same spinning disk of gas and dust that creates their host stars. Like a potter's wheel, this disk gives everything within it a uniform spin direction, or so we thought. The existence of WASP-17b forces us to confront an uncomfortable truth. Sometimes gravity plays dirty. One leading theory suggests a violent past, a gravitational tug of war with another massive planet, or even a near collision that slingshot WASP-17b into its backward trajectory. Imagine two dancers pulling each other in opposite directions until one gets flipped upside down. Alternatively, the star's gravitational influence might have warped over time due to complex interactions with its own outer layers, gradually twisting the planet's path like a cosmic lasso. There's even a chance WASP-17b didn't form in its current system at all, but was captured after being ejected from another star entirely, a wandering rogue adopted into a backward family. What makes this planet even stranger is its atmosphere. Despite its inverted orbit, WASP-17b sports puffy clouds of silicate vapor, tiny grains of sand heated to vaporized perfection floating high above its surface. Some scientists speculate these might condense into molten glass rain under the right conditions, creating a surreal weather cycle where the sky rains liquid gemstones in reverse. And because the planet orbits so close to its star, its year lasts just 3.7 Earth days, subjecting it to extreme tidal forces that stretch it into an oval shape like a cosmic egg. But the real shocker, WASP-17b might not be alone. Since its discovery in 2009, astronomers have identified a handful of other retrograde exoplanets, each one defying the so-called rules of orbital motion. Their existence suggests that planetary systems are far more chaotic than we ever imagined, with gravitational billiards matches playing out over millions of years. Some researchers now believe up to 10% of hot Jupiter's gas giants orbiting close to their stars might end up flipped, their paths scrambled by unseen forces lurking in their systems. This cosmic maverick does more than just break the mold. It shatters our assumptions about how orderly planetary systems should behave. Every backward orbit we find forces us to rewrite the textbooks, proving that the universe has a flair for the dramatic. Whether through collisions, captures, or gravitational sleight of hand, planets like WASP-17b remind us that the cosmos thrives on chaos, spinning its own rules as it goes. And somewhere out there, other celestial rebels are surely waiting to be found, their orbits cocked at impossible angles, daring us to rethink what we know. In the ancient star cluster NGC 188, a cosmic crime unfolds in slow motion. Blue stragglers, the vampires of the stellar world. These strange stars glow with the vibrant blue hue of youthful energy, burning hotter and brighter than their neighbors, yet they shouldn't exist at all. Nestled in a cluster over 6 billion years old, where every star should have aged into red giants or cooling dwarfs, these celestial outliers shine defiantly, their secret written in stolen fire. Astronomers call them stellar vampires for good reason. Blue stragglers cheat time by siphoning gas directly from companion stars, draining their lifeblood to fuel their own revival. Some do it through direct cannibalism, orbiting so close to a neighboring star that gravity peels away its outer layers, funneling fresh hydrogen into the thief's core. Others might merge entirely, colliding in a violent embrace that reignites nuclear fusion like a cosmic defibrillator jump starting a dying heart. The result? A star that looks billions of years younger than it truly is, masquerading as a newborn amid a graveyard of aging suns. NGC 188, one of the oldest known open clusters, is ground zero for these anomalies. Its blue stragglers shouldn't thrive here. The cluster's sparse environment should have prevented the close encounters needed for mass theft. Yet they persist, challenging our models of stellar evolution. Some theories suggest triple star systems might be the key. When two stars orbit tightly with a third farther out, complex gravitational dances can fling one star inward toward its partner, triggering the vampiric feast. Others propose that sheer density plays a role, with stars in crowded clusters playing gravitational pinball, occasionally smashing together in chaotic rejuvenation. What makes these stars truly fascinating isn't just their deception, it's what they reveal about stellar life cycles. By studying their light spectra, astronomers have found traces of carbon depletion, a telltale sign of material stripped from a companion's deeper layers. Some even show unusual rotation speeds, spinning faster after gorging on stolen gas, like a figure skater pulling in their arms to accelerate. The implications stretch beyond NGC 188. Blue stragglers might explain similar oddities in globular clusters and even galactic halos, rewriting the narrative of how stars evolve in crowded environments. Yet the bigger mystery remains: how many of these vampires walk among us? Current surveys suggest up to 3% of stars in old clusters could be blue stragglers. each one a cosmic chimera stitched together from multiple bodies. Their existence forces us to reconsider the quiet solitude we often assign to stars. Far from lonely beacons, many might live in violent intimacy, trading mass and light in a celestial survival game. And somewhere out there, new stragglers are surely forming, their blue glow a testament to the universe's endless ingenuity in bending its own rules. For now, NGC 188 vampires continue to burn bright, their stolen youth a flickering reminder that in the cosmos, age is sometimes just a matter of perspective, and that even stars know how to cheat time. In 2006, astronomers witnessed a stellar explosion so violent it rewrote the textbooks, SN 2006 Gi, a supernova dwarfing anything in recorded history. This wasn't just a star dying, it was a celestial body tearing itself apart with the energy of 100 normal supernovae, outshining entire galaxies for months. At its peak, it blazed with the luminosity of 50 billion suns, a flash so intense it could have briefly outshone the Milky Way if placed at its core. The aftermath left scientists stunned. How could a single star unleash such apocalyptic fury? The leading suspect is a process called pair instability, a runaway thermonuclear reaction only possible in the universe's most massive stars, those born with over 140 times the Sun's mass. Unlike typical supernova, where a collapsing iron core triggers the explosion, pair instability supernova begin with a far stranger chain of events. Inside these titanic stars, temperatures and pressures grow so extreme that gamma-ray photons, the very particles carrying light, spontaneously transform into matter, electron and positron pairs. This conversion steals energy from the star's core, destabilizing the delicate balance between outward pressure and gravity's inward crush. Without warning, the core implodes, igniting a chain reaction that doesn't just explode the star, it annihilates it, leaving no black hole or neutron star behind. Just nothing. SN 2006 Gi's light curve held smoking gun evidence for this theory. It stayed bright far longer than normal supernova, suggesting an unusually large amount of radioactive nickel, 50 times more than typical explosions, was forged in the blast. This aligns perfectly with pair instability models where the entire star, not just its core, becomes fuel for the fire. But here's the eerie part, we might be sitting front row for an encore. 20 times closer to Earth lies Eta Carinae, a hypergiant star so unstable it makes SN 2006 Gi's progenitor look tame. In the 1840s, it erupted in a false supernova event, ejecting enough material to form 10 suns yet somehow surviving. Today, it's a ticking time bomb wobbling on the edge of pair instability itself. Should Eta Carinae follow SN 2006 Gi's path, its explosion would be bright enough to read by at night, visible even in daylight for weeks. The fireworks wouldn't stop there. Its blast wave could shred nearby nebulae, trigger new star formation, and bathe our solar system in enough radiation to temporarily alter Earth's upper atmosphere. Yet for all their violence, these supernovae are cosmic alchemists. The same forces that obliterate stars also seed the universe with heavy elements: oxygen, carbon, even gold, flinging them into space at incredible speeds. SN 2006 Gi's remnants, now expanding into a nebula 7 times the size of Pluto's orbit, are proof of this recycling. Its destruction forged the very materials that might one day form planets or even life. What's most humbling is the scale of these explosions. A typical supernova can outshine its host galaxy for weeks, but pair instability events like SN 2006 Gi operate on another level entirely. They're the universe's way of testing its own limits, pushing stellar physics until the rules break. And somewhere out there, other monsters like Eta Carinae are counting down to their own spectacular ends, each one a reminder that even the brightest lights in the cosmos are fleeting, burning brief and brilliant before vanishing into the dark. Drifting through intergalactic space like a phantom, the mysterious object known as HI 21cm high-velocity cloud defies every expectation of what a galaxy should be. This colossal structure, stretching thousands of light-years across, contains enough hydrogen gas to form millions of stars, yet scans reveal nothing but darkness. No stellar nurseries, no glittering suns, just an eerie void where a galaxy's heartbeat ought to be. Its name comes from the telltale radio signature of hydrogen atoms, detectable only because they occasionally release photons at the 21-centimeter wavelength, a faint whisper betraying the cloud's otherwise invisible presence. The question haunting astronomers isn't just what this object is, but how it stubbornly refuses to play by the rules. Most gas clouds this massive collapse under their own gravity, igniting star formation in a chain reaction. Yet HI 21cm high-velocity cloud has lingered for billions of years, its gas too turbulent or diffused to coalesce. Some researchers argue it's a failed galaxy, a relic from the early universe that lacked the dark matter needed to compress its gas into stars. Without the gravitational scaffolding that normal galaxies possess, its hydrogen simply drifted, frozen in perpetual potential. Others propose a more violent origin, the shredded remains of a galactic collision, torn apart by tidal forces and left to wander as cosmic flotsam. Clues might lie in the cloud's motion. Unlike most interstellar gas, which orbits predictably around galactic centers, this object barrels through space at hundreds of kilometers per second, hence its high-velocity designation. Such speed suggests it could be debris from a long-ago encounter, perhaps ejected during a titanic clash between galaxies. Supporting this, some simulations show similar structures forming when smaller galaxies are ripped apart by larger neighbors, their stars captured but their gas flung outward like a splash from a stone tossed into water. Yet the most tantalizing theory involves dark matter's elusive role. If HI 21cm high-velocity cloud is indeed a failed galaxy, its lack of stars implies its dark matter halo was unusually feeble, preventing the gas from ever condensing. That would make it a rare fossil from the universe's formative years, a glimpse into how most early proto-galaxies fizzled out before lighting their first stars. Alternatively, if the cloud is collision debris, its persistence challenges assumptions about how quickly such gas should dissipate or merge with other structures. Either way, its existence forces us to reconsider how galaxies live, die, and sometimes linger in limbo. What makes this dark galaxy particularly haunting is its potential to rewrite the story of cosmic evolution. If large, starless gas clouds are more common than we've detected, they could represent a hidden population of stealth galaxies, their mass skewing our calculations of the universe's total matter. Some might even drift closer than we realize. In fact, a similar high-velocity cloud orbits the Milky Way, and astronomers debate whether it's a satellite galaxy in its own right or just passing debris. For now, HI 21cm high-velocity cloud remains an enigma, a shadowy reminder that the universe teems with unseen structures. It challenges the very definition of a galaxy, proving that gravity's tapestry includes threads we're only beginning to discern. And somewhere in the darkness, other ghostly clouds likely drift, their stories written not in starlight but in the silent radio whispers of cold, lonely hydrogen. Imagine a world so light and airy you could theoretically hold it in your hands if it weren't scorching hot and the size of Jupiter. WASP 107b isn't just another gas giant. It's a cosmic enigma, a planet with the density of cotton candy, defying every expectation of how planetary physics should work. Orbiting its star every 6 days, this puffy oddball weighs in at just 1/10 Jupiter's mass despite being roughly the same size, making it one of the least dense exoplanets ever discovered. To put that in perspective, if you could compress WASP 107b to the density of water, it would float like a beach ball in an ocean, except this beach ball has a surface temperature hot enough to vaporize metal. How does such a fragile world even hold itself together? The secret lies in its inflated atmosphere, a bloated cloak of hydrogen and helium stretching tens of thousands of kilometers into space. Unlike compact gas giants like Jupiter, where gravity compresses the atmosphere into dense layers, WASP-107b's weak gravitational grip, about 1/30th of Earth's, allows its gases to puff outward like a cosmic soufflé. But here's the puzzle. With gravity this feeble, the planet's atmosphere should have evaporated into space eons ago, leaving behind a barren core. Yet Hubble observations reveal a thriving, extended atmosphere, rich with water vapor and other molecules stubbornly clinging to existence. One theory points to an internal heat source, possibly tidal forces from its star stretching and squeezing the planet's interior, generating enough energy to keep the atmosphere inflated. It's like blowing on a dandelion repeatedly to prevent its seeds from scattering. Alternatively, WASP-107b might have formed farther out in its system, where cooler temperatures allowed it to accumulate an unusually thick gas envelope before migrating inward. As it moved closer to its star, the intense radiation heated and expanded its atmosphere like a balloon left in the sun, but somehow it never popped. The planet's fluffy structure also hints at a bizarre core. Most gas giants have solid or liquid centers dozens of times Earth's mass, but WASP-107b's core might weigh as little as 4 Earth masses, barely enough to anchor its gargantuan atmosphere. Some models suggest the core could even be porous, riddled with caverns or icy layers that reduce its overall density. Imagine a sponge the size of a planet, its hollow spaces filled with swirling gases instead of water. What makes WASP-107b truly revolutionary isn't just its defiance of gravity, it's the window it offers into planetary diversity. For decades, astronomers assumed all gas giants resembled Jupiter or Saturn, but this cotton candy world proves planets come in recipes we've never dreamed of. Its existence suggests that stellar systems might craft planets along a spectrum of densities, from super-Earths as dense as iron to these ethereal, hot fluffies barely more substantial than mist. And the implications stretch beyond curiosity. Planets like WASP-107b challenge our tools for studying exoplanet atmospheres. Their puffy, extended envelopes make them ideal laboratories for analyzing chemical compositions, as their gases are more accessible to telescopes than the tightly bound atmospheres of denser worlds. Already, researchers have detected helium streaming from WASP-107b's outer layers like a cosmic comet tail, a phenomenon that could teach us how planets lose their atmospheres over time. Yet for all its strangeness, this camouflage planet might not be rare. As telescopes grow more sensitive, we're finding entire populations of low-density worlds, each one a reminder that the universe has a flair for the extravagant. From diamond planets to flaming ice worlds, the cosmos keeps rewriting the rules, proving that when it comes to planetary design, imagination is the only limit. So the next time you bite into cotton candy, remember, somewhere out there, an entire world floats on the same fragile physics, spinning silently under the glare of an alien sun. Most supernovas blaze to life within galaxies, their final moments playing out against backdrops of swirling stars, but SN 1000 plus 0216 broke all the rules. This cosmic maverick detonated in the loneliest place imaginable, the abyss between galaxies, a void so empty it took scientists years to confirm they weren't seeing a glitch. At 9 billion light-years away, its light reached us not from some bustling galactic neighborhood, but from the frigid emptiness where stars rarely venture. The discovery sent shockwaves through astronomy, because if stars can explode in the intergalactic wilderness, our understanding of stellar life cycles might be missing a crucial chapter. So how does a star end up stranded in the cosmic boonies? One theory suggests it was flung there by unimaginable forces. Picture a binary star system wandering too close to a supermassive black hole. The black hole's gravity could rip the pair apart, capturing one star while hurling its companion into the void at speeds topping 2 million miles per hour, fast enough to escape its galaxy forever. Alternatively, this star might have belonged to an ultra-faint dwarf galaxy, one so small and dim that a close encounter with a larger galaxy stripped away its stars like feathers in a hurricane, leaving this lone wanderer adrift. But here's the real puzzle. Exploding alone changes everything. Supernovas in galaxies are surrounded by gas and dust, their shockwaves plowing into these materials to create glowing remnants that linger for millennia. SN 1000 plus 0216 had no such canvas. Its explosion likely illuminated nothing but a few stray hydrogen atoms, its light fading into the void without fanfare. Yet that isolation makes it invaluable. Without galactic gas to distort its signature, astronomers could study its pure, unaltered spectrum, a rare opportunity to decode the physics of stellar death without interference. The explosion itself was another enigma. Most solitary stars in intergalactic space are ancient red giants or white dwarfs, yet SN 1000 plus 0216's light curve suggested something far more massive, a Wolf-Rayet star perhaps, a blue giant so unstable it sheds entire solar masses of material before collapsing. If confirmed, it would mean these volatile behemoths can survive and die far from the stellar nurseries that birthed them, challenging assumptions about where heavy elements forge. What's truly humbling is the scale of its loneliness. For context, if the Milky Way were the size of North America, SN 1000 plus 0216 detonated somewhere over the Pacific Ocean, not just offshore but midway to another continent. Its light traveled for 9 billion years through near-total darkness before reaching us, a single flare in an ocean of nothing. Yet this supernova might not be unique. Surveys suggest up to 15% of stars could exist outside galaxies, ejected by gravitational chaos or born in failed dwarf galaxies. If even a fraction of these go supernova, the intergalactic void might flicker with invisible fireworks, transient beacons in the dark, rewriting the story of where and how stars live and die. SN 1000 plus 0216 isn't just an oddity, it's a preview. The cosmos is vaster, stranger, and more defiant of boundaries than we ever imagined. At the heart of the Perseus galaxy cluster, NGC 1275 wages a silent war against cosmic entropy, not with gravity or light, but with magnetism on a scale so vast it defies logic. This monstrous elliptical galaxy, also known as Perseus A, weaves a web of magnetic fields stretching over hundreds of thousands of light years, strong enough to grip its iconic filaments of gas like cosmic puppet strings. These delicate tendrils, some as long as the Milky Way's diameter, should have disintegrated billions of years ago under the cluster's extreme conditions. Yet they persist, glowing with ethereal beauty because NGC 1275 magnetic architecture refuses to let them fade. What makes these fields so extraordinary is their endurance. Magnetic forces typically dissipate over cosmic timescales, their energy bleeding away into the void. But NGC 1275 fields regenerate continuously, fueled by a vicious cycle of galactic turmoil. At its core, a supermassive black hole spews jets of charged particles at nearly light speed, while the galaxy itself cannibalizes smaller neighbors, stirring the surrounding plasma into a froth of electric currents. This chaos acts like a dynamo, twisting and amplifying magnetic lines until they form a galaxy-sized shield, one that not only preserves the filaments but sculpts them into their eerie, thread-like shapes. Hubble's images reveal the filaments in stunning detail, ropes of ionized gas glowing red with hydrogen alpha emissions tangled like a cosmic spiderweb. Without magnetism, these structures would have either collapsed under their own weight or been shredded by the cluster's violent environment. Instead, the fields act as a scaffold, channeling and stabilizing the gas with invisible force. Imagine trying to suspend a cloud of smoke in midair using only static electricity, except here, the cloud is light years across, and the static is a magnetic grip stronger than anything we could replicate on Earth. The real mystery lies in how these fields remain so organized. In most galaxies, magnetic lines chaotically crisscross like scribbles on paper, but NGC 1275 fields show eerie coherence, aligning along the filaments with almost artistic precision. One theory suggests the black hole's jets act like cosmic knitting needles, dragging and stitching the fields into order as they punch through the surrounding gas. Another proposes that the galaxy's relentless mergers constantly comb the magnetism, smoothing out tangles while injecting fresh energy. What's at stake isn't just a pretty cosmic light show. NGC 1275 magnetic monster challenges our understanding of how galaxies evolve. Its fields transport energy across vast distances, heating gas that would otherwise cool and form stars, effectively putting the brakes on galactic growth. They may even shield the galaxy from the Perseus cluster's searing plasma, creating a bubble of relative calm in a maelstrom of superheated particles. If similar magnetic megastructures exist in other clusters, and there's growing evidence they do, they could explain why some galaxies age so differently than our own. Yet for all their power, these fields leave traces we're only beginning to decode. Radio telescopes have mapped their faint whispers, revealing patterns that mirror the filament's curves. X-ray observations show gaps where magnetic pressure pushes back against the cluster's gas, like an invisible hand pressing against a curtain. Each new dataset peels back another layer, showing how magnetism, often overshadowed by gravity in cosmic dramas, can rule entire galaxies when conditions align. So while NGC 1275 black hole steals headlines for its explosive jets, the real maestro might be the galaxy's hidden magnetic force, an ancient, persistent hand shaping its destiny from the shadows. It's a reminder that the universe doesn't just build with gravity and fire, but with subtler, equally potent tools, crafting order from chaos one thread at a time. At the outer edges of what physics says should be possible spins a cosmic top so fast it could outrace a kitchen blender. PSR J 1748-2446 AD, a pulsar whirling 716 times every second. That's not just rapid, it's borderline impossible, a neutron star spinning so violently that its surface moves at nearly 1/4 the speed of light. At that rate, the centrifugal forces should tear it apart, scattering its ultra-dense material across space like a shattered flywheel. Yet somehow, against all expectations, this stellar remnant holds together, bending the known laws of physics to their breaking point. What keeps this pulsar from self-destructing is a delicate balance between two titanic forces. The first is gravity, the same crushing weight that forged the neutron star in the first place, packing a dying star's mass into a sphere no wider than Manhattan. This gravity is so intense that a sugar cube-sized chunk of its matter would weigh as much as Mount Everest, but pulling against it is the absurd rotational energy, trying to fling material outward like a merry-go-round gone berserk. Normally, neutron stars max out around 600 rotations per second before they'd theoretically fly apart. PSR J 1748-2446 AD laughs at that limit, spinning faster than any other known pulsar, sustained by a combination of perfect density, flawless symmetry, and possibly a core of exotic matter we've yet to understand. The origins of this speed demon are as fascinating as its survival. Most pulsars are born when massive stars collapse, their cores compressing so tightly that protons and electrons fuse into neutrons, releasing a burst of energy that kicks the newborn star into a rapid spin. But to reach 716 revolutions per second, nearly twice as fast as a typical kitchen blender, this one likely had help. Astronomers suspect it's part of a binary system where it vampirically siphoned gas from a companion star, each stolen sip transferring angular momentum and accelerating its rotation like a figure skater pulling in their arms. The real miracle is that the accretion process didn't push it past the point of no return. Here's where it gets even stranger. The pulsar's magnetic field plays bouncer to this chaotic dance. While all neutron stars have powerful magnetism, this one's rapid spin amplifies the effect, generating a field that channels escaping particles into focused beams radiating from its poles. These beams sweep across space like lighthouse beams, emitting pulses of radio waves detectable across thousands of light years. It's this precise blinking that lets astronomers clock its rotation so accurately, each pulse arriving with metronomic regularity, a cosmic stopwatch ticking 716 times per second. But the implications stretch far beyond setting records. PSRJ 1748-2446 AD serves as a natural laboratory for states of matter that can't exist on Earth. At its core, pressures may be so extreme that neutrons themselves break down into a soup of quarks, a theoretical substance called quark-gluon plasma that hasn't been seen since the universe's first microseconds. Alternatively, its core might contain hyperons, exotic particles infused with strange quarks that could rewrite our understanding of particle physics. Every extra rotation it manages hints at unknown forces holding atomic nuclei together under conditions we can't replicate. Yet even this pulsar won't spin forever. Over millennia, its emissions of particles and gravitational waves, ripples in space-time caused by its slight imperfections, will slowly drain its energy like a top wobbling to a halt. But for now, it defies expectations, a beacon of extreme physics proving that when it comes to the universe's rules, there's always room for an exception. And somewhere out there, another pulsar might be spinning faster still, waiting to remind us how much we have yet to learn. Right now, as you watch this, an invisible storm is passing through you, trillions of ghostly particles called neutrinos, streaming from the most violent events in the universe. Born in the hearts of exploding stars, black hole jets, and colliding galaxies, these subatomic phantoms travel billions of light years unimpeded, piercing planets' walls and even your body like you're made of air. Every second, over 100 billion neutrinos from the sun alone flood through every square centimeter of your skin. Yet you'll never feel them because neutrinos barely interact with matter, a trait that makes them cosmic riddles wrapped in enigmas. But in 2013, humanity finally caught one. Deep beneath the South Pole, a detector called IceCube trapped a neutrino unlike any other. Unlike solar neutrinos, which arrive in predictable waves, this one carried an energy so staggering, over 1 quadrillion electron volts, that its origin could only be something cataclysmic, a supermassive black hole's jet 4 billion light-years away in a galaxy called TXS 0506+056. The discovery marked the first time we'd pinpointed an extragalactic neutrino source, opening a new window into the cosmos. How do you catch something that slips through solid lead like mist? IceCube's design is as ingenious as it is massive. Embedded in a cubic kilometer of Antarctic ice are over 5,000 light-sensitive modules, waiting for the rare moment a neutrino collides with an atom. When that happens maybe once every few hours, the impact spawns a charged particle moving faster than light can travel through ice. This creates a shockwave of blue Cherenkov radiation, a faint glow that the detectors trace back to the neutrino's path. It's like capturing the shadow of a bullet too fast to see. The TXS 0506+056 detection was a watershed because it linked high-energy neutrinos to blazars, galaxies whose supermassive black holes fire particle jets directly at Earth. This particular neutrino's energy hinted at unfathomable forces, perhaps protons accelerated near the black hole to velocities within a hair's breadth of light speed. When those protons smashed into interstellar gas or light, they likely spawned pions, unstable particles that decay into neutrinos. That single ghostly messenger, after traveling 4 billion years through darkness, carried proof of physics at its most extreme. What's wildest is how many neutrinos slip through the net. For every one ice cube catches, billions more pass cleanly through Earth. Some might be from the Big Bang itself, relics of creation still haunting the cosmos. Others could be forged in processes we haven't even discovered yet. Their reluctance to interact makes them maddeningly elusive, but also invaluable. Unlike light, neutrinos aren't scattered by dust or bent by magnetic fields. They travel in straight lines from their origins, offering pristine snapshots of events obscured to telescopes. Imagine using these ghosts as cosmic messengers. Future neutrino observatories could map the universe's most violent engines by their faintest signals, like eavesdropping on black holes through whispers. They might even solve dark matter mysteries if certain theoretical particles decay into neutrinos we could detect. Every one that flickers into existence in Ice Cube's icy vault carries a story of a star's last gasp, a black hole's hunger, or perhaps something entirely unknown. So the next time you glance at the night sky, remember, you're not just a spectator, you're a landing site for invisible rain, a living detector in a storm that's lasted since the first stars lit the cosmos. The universe isn't just above you, it's passing through you, one ghostly particle at a time. The universe has a light problem, specifically a missing light problem. Scientists call it the photon underproduction crisis, and it's one of the most puzzling discrepancies in modern cosmology. Here's the issue: when astronomers run simulations of the universe's structure, they predict a certain amount of ultraviolet UV light should be floating between galaxies, emitted by quasars, young stars, and other energetic sources. But when they point telescopes at the cosmos and tally up the actual photons, the numbers don't add up. There's far less UV light than there should be, as if someone turned off half the lights in the universe and forgot to tell us. So where did all that light go? One possibility is that our simulations are flawed. Maybe we've overestimated how much UV radiation stars and quasars produce, or misunderstood how it spreads through space. But the leading hypothesis is far more intriguing. The missing photons might be getting swallowed by something we can't see. Vast clouds of cold, dark gas could be drifting between galaxies, absorbing UV light like a cosmic sponge. These wouldn't be ordinary gas clouds. They'd need to be rich in molecules like hydrogen or helium, dense enough to intercept photons but too diffuse to emit detectable light of their own. The implications are staggering. If these invisible absorbers exist, they could represent an entirely overlooked component of the universe's matter budget, a hidden reservoir of gas that doesn't fit neatly into our current models. Some researchers speculate this material might be tied to the elusive, missing baryon problem, where observations suggest about half the universe's ordinary matter, the stuff that makes up stars, planets, and us, remains unaccounted for. These ghostly gas clouds could be hiding it in plain sight, camouflaged by their own darkness. But there's another twist. The missing light might not be missing at all, just transformed. UV photons don't vanish when absorbed. They're re-emitted at lower energies, often as heat. If this process is happening on a cosmic scale, the energy could be lurking as a faint, uniform glow in the far infrared spectrum, a background hum too subtle for current telescopes to distinguish from noise. Future instruments like the James Webb Space Telescope's successors might finally spot this hidden radiation, turning the crisis into a breakthrough. What makes this mystery so compelling is how it forces us to question our assumptions. For decades, we've mapped the universe by the light we can see, trusting that brightness correlates with reality. But the photon underproduction crisis suggests we're only seeing half the story, that the cosmos might be far murkier, filled with shadowy structures that subtly shape the light passing through them. It's a reminder that even in an age of advanced telescopes and supercomputers, the universe still holds back secrets, waiting for us to ask the right questions in the right light. From stars that cheat death to invisible storms of particles passing through your body this very second, the universe has shown us its endless capacity for wonder. We've explored planets made of diamond, galaxies cloaked in darkness, and black holes that sing in notes deeper than human hearing can fathom. Each discovery peels back another layer of cosmic mystery, proving that reality is far stranger than anything we could invent. Who could have imagined a cloud in space smelling of rum and raspberries, or a rogue black hole hurtling through the void, trailing newborn stars in its wake? These aren't just curiosities, they're clues, forcing us to rewrite the rules of physics and rethink what's possible. The true gift of these revelations isn't just spectacle, it's perspective. Every time we uncover a new paradox, like the two-faced star Janus or the phantom galaxy Dragonfly 44, we're reminded how much remains hidden. The universe isn't just vast, it's layered with secrets tucked inside secrets. Even the coldest corners, like the Boomerang Nebulas near absolute zero chill, or the hottest extremes, like pair instability supernovas outshining galaxies, challenge our definitions of normal. And let's not forget the photon crisis, proof that we might be missing half the light in existence, swallowed by shadows we've yet to map. But here's the beautiful part, this story isn't finished. Every oddity we've uncovered, the diamond rains, the hypervelocity stars, the magnetic puppeteer galaxy NGC 1275, is a thread begging to be pulled. Maybe you're the one who'll crack the mystery of the Great Attractor or decode the whispers of neutrino storms. That's the thrill of cosmic exploration. The next revelation could come from anywhere: a backyard telescope, a lab experiment, or even a comment left below. So tell us, which fact rewired your brain? Was it the alcohol cloud vast enough to drown civilizations, or the planet reflecting starlight like a cosmic mirror? Drop your favorites in the comments, or take it further, pitch your wildest theory about where these puzzles lead. After all, the universe doesn't reveal its secrets to those who stop asking questions. Stay hungry, stay curious, and keep looking up. The next great cosmic surprise, it's out there waiting.